let's quickly jump into seed exercise. We need to finish this one as soon as possible. So seed exercise, filter design and verification and sampling, which is CAD4 and CAD5. Go to CAD4, which was second order low pass filter, 1 dB Chebyshev second order low pass filter design. So using this kind of Sallen-Key low pass filter design, second order Chebyshev 1 dB, sorry, low pass filter. So you can have a look on this Texas Instruments application document, for example, here. And as we discussed in the discussion forum, you can study all of them, but what is key idea about designing the Sallen-Key filter was this. So if you want to design 1 dB Chebyshev filter in second order, then you need to design Q factor equal to 0.95. Of course, it must be closer to 9565 and so on and so on, but we set tolerance range as 0.94 to 0.96 as a LOP tolerance or LOP estimate. Then let me first open RC low pass filter. Okay. This simulation setup is basically same as we did last time for CAD3. So let me make it more tidy. So I prepared some Sallen-Key filter characteristics that we discussed during this quiz time. You probably also can do the similar way using the equation of actual Q factor as we discussed in lecture 5. So those are the parameters and scripts that I used, but let me go one by one again. Because in the first question, based on the output capacitance range available from the amplifier, which you designed in CAD exercise 2, or you can also redesign it, calculate the resistance and capacitance values required to achieve F0 equal to 100 kilohertz for this second order low pass filter. So in CAD exercise 2, we designed a buffer with the output capacitance. It must be larger than, depending on your design, but in my case, it was must be larger than 50 femtofarad to ensure a certain amount of, let's say, 50 degree or 60 degree phase margin. So let me first run this Python script. So this is just importing the necessary packages. And let's target to derive and get the theoretical values to achieve 100 kilohertz cutoff frequency. So we can use this equation. So here, let me put resistance equal to 1 mega ohm as a LOP estimate, and C1 equal to 1 pico, and C2 equal to also 1 picofarad. And here is cutoff frequency equation. So there's nothing special. So I just applied pi, which is 2 pi. This is a 1 over 2 pi. And R is there. And numpy square root C1 times C2. So indeed, the actual equation is, let me see. Yeah, so actual equation is 1 over 2 pi times 1 over square root R1, R2, C1, C2. And when we assume R1 is equal to R2, then 1 over R times square root C1, C2. So this is the equation here. And let me copy this one. So So we get capacitances C1 and C2, and the F0 is 159.15 kilohertz, very close to 100 kilohertz. But if we just put, R equal to some sort of 1.5915, then we can make 100 kilohertz. So we already solved this one, right? And before we go through the simulations, let's finish our calculations of expected, the ideal Q factor and the actual Q factor. So here, let me copy and paste. So the ideal Q factor is indeed 0.5 times square root C1 over, this one is C2. And the actual Q factor, as we went through today in today's quiz, so actual Q factor, when we take R1 equal to R2, then the ideal Q factor, 1 over ideal Q factor plus 2 times ideal Q factor over 1 plus open loop gain is denominator part. And we haven't defined open loop gain. So in my case, the open loop gain was as large as 30 dB. In my amplifier design. So I put 29.575 after running the AC simulation of open loop gain. And then let me run this script. Okay. Then we can calculate the ideal Q factor when we set C1 equal to C2, then 0.5, but the actual Q factor is slightly lower than ideal Q factor, which is 0.492. So we want to make Q factor equal to very close to 0.95. So let's try to make it. So in this case, we can increase ideal Q factor by increasing C1. What about times 2? And all right. So if we just change C1 only, then it will also change F0, which is not our expected result. So that is the point where I put, so let's say ARPA equal to 2. Then when we multiply ARPA in C2 and multiply ARPA to C1 and divide ARPA to C2, then we don't change the F0 natural frequency, but we are changing the Q factor. Then yeah, the ideal Q factor equal to 1 and the actual Q factor equal to 0.94. So slightly larger value. What about this? Or maybe here. Yeah, then 0.956 is achieved. So with this condition, let's go back to the simulation. So we can put 1.5915 mega and C1. Let me see if I have load cap. No, I don't have load cap, so delete. I put just a bias current as the same as CADa exercise 2, and the DC of bias voltage as 0.4 volt, and C1 capacitance 2.04 picofarad, and C2 capacitance 490 femtofarad. So with this condition, let's run the simulation. Sorry. Let's put 0. then you can see that its cutoff frequency, the natural frequency deviates from our expectation, and the Q factor is also deviating. So this is because, we tried to model actual Q factor as much as possible, but F0 is also deviating. This is because of this is too small. This is because of the parasitic capacitance that is connected to the amplifier's input side and the parasitic capacitance that is connected to amplifier's output side. So to get some idea about what is going on about this parasitic cap, so you can check. Okay, you can go inside and check the DC operating point of this transistor. Then you can check the CGG term, which is 55 femtofarad. So CGG is basically, as we introduced during CADa exercise 2, the total capacitance that is connected to here, and the body here, and source here, and the total capacitance that is seen at the gate side. Of course, it doesn't necessarily connect it to ground, no, but it's still very rough estimate of the total capacitance that is connected to the ground. So 55, let's put. C2, let's say actual, is equal to C2 plus 55 femtofarad. And let's see what happens. Okay, we need to change this one. Actual. And actual. So yeah, it is changing, right? And it is very close to what we expect, 94 kilohertz, which is 93 kilohertz. And the actual Q factor is pretty much closer to 0.912, 0.908. But for accurate analysis, let's try to match it. So in this case, we can increase the parasitic cap, modeled parasitic cap. So yeah, so then it's very close to each other, right? 93 kilohertz here, and 93 kilohertz, and 0.901, 0.908. So with this modeling, we can control our alpha or resistance. So let me control the alpha first. If we increase alpha, then we can actually increase the Q factor here. 2. Okay, and it touches 0.959, but it's too much closer to what we defined as a tolerance range. So let's slightly decrease it. Okay, this is good. And then now we have to tune the natural frequency, so we can decrease this resistance value. Probably about this. Okay. No, the other way around. Okay, good. So we can use these parameters. So for 9 mega ohm, and the C1 capacitance should be 19, and C2 capacitance should be 456 femtofarad. And let's see what happens. Okay, nicely it is matching to the expectation, right? But still it deviates from our tolerance. So let me slightly increase it. Okay, then it's too close. Yeah, so yeah, let's just say we satisfy this requirement tolerance. So then in this case, in this situation, then let's go through the AC simulation. So plot the magnitude response. Let me go out. And for the magnitude, so here, and our cutoff frequency was 100 kilohertz, so 100K. So it says 892. And actually, we discussed last time that the second order low pass filter at omega equal to omega 0, the magnitude should be equal to Q factor, right? And our Q factor is actually 0.595. But it is a slightly deviating from our expectation. This is because of finite the open loop gain. So because of finite open loop gain, let me see. So let me copy and paste here. Closed loop gain is open loop gain over 1 plus open loop gain. And let me print this one also. The closed loop gain at the DC level is equal to 967. It is very close to what we are looking at, 968. So because of this kind of limited open loop gain, so there is some discrepancy of theory and the simulated result. But it's not deviating like more than twice or more than 30% or something. So you can calculate the deviation in terms of percent of error here, right? And we can run the pole zero simulation. I already have run pole zero simulation. Identify two pole frequencies of the filter from PZ simulation result. PZ, and let's just plot poles only. Then there are some poles, right? But those poles here, this is a megahertz range. So we were looking at the kilohertz range. So we don't want to worry about too much about these high frequency poles. Let's limit our access to 200 kilohertz. Then you can find by zooming in, you can find the two pole frequencies, which is the real value is around 50 kilohertz. So you can do all of this, like two pole frequencies and the natural frequency and Q factor. I already did based on the internal calculator. And you can also double check by calculating the theoretical method for getting the real value and the imaginary value. And then let's run the transient simulation. I already did the transient simulation here. And let's see. Transient voltage. Okay. So one thing I would like to mention that I miscalculated last time was that we can actually run lifetime by doing the calculator, the internal calculator. So the starting point is 406 and the end point is starting point is 406 and end point 454. So final value is 54 here, and we run it. Then you can see that the rise time is 10% to 50%, 10% to 90% rise time is 2.824 microsec. So for this, you can verify again. So for the delta value, delta dy here, dy, is 48 millivolt, so 48. And the initial value is 406 millivolt, and final value is 454 millivolt. And the 10% value is initial value plus delta times 10%. And the 90% is initial value plus delta times 90%, I mean 0.9. So the calculated result is 410 millivolt to 450 millivolt. So 410 millivolt to 400, what's it? 449, almost 450, like this. 250. So this is very close to what we calculated for the rise time, 2.8 microsecond. And this behavior is definitely underdamped, right? So the damping factor is less than 1 because it has a ringing effect. So if you remember, how can I draw it? So if the damping factor is less than 1, then there is a sine term in transient step response, right? So this is a sine term because of the damping factor. If the damping factor is larger than 1, then there is no sine term, and the two poles are real poles. It doesn't create any imaginary complex conjugate. So based on this result, now we can go through the simulation versus theory. So the right side, we have the AC result. So we can export this. So let's call CD4 AC. Of course, it doesn't necessarily need to be like always this way. You can choose whatever you feel like easier for your method. For example, MATLAB. That's fine. Then you can see that at least for the low frequency part, it is aligning nicely for the red part and the theory part, which is a black part. Actually, I haven't discussed this much, but in theory, the Chebyshev 1 dB filter has slight the gain reduction at the DC range. So you can see that the red line, which is stimulated line, is higher than the black line theory or the DC gain. So this is theoretical limit. Of course, this is fine. I mean, even if you couldn't catch it, there's no kind of point reduction. But let me introduce what is happening. So we can normalize the DC gain to be matched to 0 dB. And you can see that it's more closer to matching to the theory, Chebyshev 1 dB. Of course, there is some kind of weird behavior, right? It is deviating here and then going back towards like this kind of shape. You can verify later. This is happening because of the fundamental limit of Sallen-Key low pass filter. So suppose we are taking S equal to infinite. It is very, very high frequency. Then this one is short circuit capacitor. This capacitor is also short circuit. Then the transfer function is actually happening as from input side, resistor, and this one is ground. And we are connecting like equivalent output resistance and ground and the output. So what is happening is that this is also introduced in the application document of Texas Instruments. Input R and R. and the output impedance of the amplifier, Z out, and let's make a connection, V out. So there is a finite high frequency gain. So it doesn't go to negative infinity, but it touches to the limit. So that is the effect of what you probably are experiencing at the tail of the high frequency part. But what is most important thing is that how it is matching to the expectation around this corner frequency. So if you successfully matched this behavior around the low pass filter corner frequency, then everything is good. Okay, now let's move on to the step response. For the step response, we can similarly do copy, and here let's make CAD4 step, paste here, step, then yeah, you can see that it is at least for the overall response, how it is leaning or how it is behaving, going up and down, is very, very close to the theoretical expectation, right? But for better modeling, we can do. So the initial point is 406 millivolts, and the delta value here, delta value is 48 millivolt. So 48 millivolt. Then it becomes slightly closer to the theory. And the left thing to do is modeling the finite theoretical gain reduction at the low frequency. In theory, the Chebyshev 1 dB response has a slight DC gain reduction, as I discussed. So to model this, I think for this one, yeah, so we can divide by 10 to the power of magnitude 0 over 20. So this one, magnitude 0 is meaning here. So magnitude of dB scale of theoretical 1 dB Chebyshev filter. So we need to first convert it back to the linear scale by using this equation, 10 to the power of dB scale over 20, and then divide it. Then you can see that it nicely matches, very close to our simulated results. Of course, there are some deviation because the theoretical Chebyshev 1 dB filter should have exactly equal to Q factor equal to 0.95, like 6 or blah, blah, something. So you can try to match it as much as possible. Okay, so this was the CAD exercise 4, right? Discuss how well your filter matches the theory.